and immense pleasure, I, Dr. P. Malati, Associate Professor, Department of Data Analytics, Saveetha College of Liberal Arts and Sciences, feel privileged to extend our warm welcome to today's resource person, Dr. L. Shobana, Associate Professor, Department of Mathematics, SRM Institute of Science and Technologies, Kottankulathur. And I also welcome all the participants from various reputed institutions to the Virtual Faculty Development Program on Graph-Based Technique in Secure Network Cryptography. Let me introduce our university. Saveetha Institute of Medical and Technical Sciences is a key contributor to quality education in India. With an array of specialization such as medicine, dentistry, allied sciences, engineering, law, management, physiotherapy, pharmacy, nursing, physical education, architecture, and liberal arts and sciences. SIMATS has been ranked A++ grade by NAC, 13th rank by NIRF, and band A from Atal ranking of Institution on Innovation Achievements. SIMATS is World Ranking 2023 for excellence in academics, employability, and startup ecosystem, and in research. Saveetha College of Liberal Arts and Sciences, a well-regarded constitute college of Saveetha Institute of Medical and Technical Sciences, has been established in the year 2020 with an objective to craft the world's best college in the liberal arts and sciences discipline. Higher education magazines ranked Saveetha College of Liberal Arts and Sciences among the top 10 promising colleges in Chennai 2023. Today, the college offers various undergraduate programs in liberal arts and sciences like BCom General, BCom A&F, BCom A&F with PA, BCom CS, BBA, BCA, BSc CS, BSc AADS, BA Bharadam, affiliates integrated courses, MSc Biotechnology, and MSc Bioinformatics. The college has experienced faculty, excellent infrastructure, integrated with eminent research teams. The college offers study abroad programs with universities in UK, Malaysia, Singapore, Australia, Indonesia, UAE, and etc. On behalf of Department of Data Analytics, we extend our profound gratitude towards our respected Chancellor of SIMATS, Dr. N.M. Veerayan Sir, respected Director Academics, Dr. Deepak Sir, Dynamic Director Madam, Dr. Ramya Deepak, and Vice Chancellor. We wish to express our heartfelt gratitude to our Principal Madam, Dr. Gunita Arun Chantok, who gives direction to every student and faculty members. This is an occasion we get opportunity to test our knowledge and understanding. It is a moment of knowledge, speak but wisdom listens. Now I call upon Mr. Kalai Professor and Head of the Department of Data Analytics to introduce the resource person.
Thank you, Malati ma'am. I'm very happy to introduce today's resource person, Dr. L. Shobana, to our FDP. She has gained around 17 years of experience in the teaching field, and she is presently work as an associate professor in the Department of Mathematics, SRM University, Kottankulathur, and her area of specialization, graph labeling, automata and formal languages, number theory, cryptography. And she has a research guidance. She has a guided MSc projects, 3 students, and she also guide the PhD students. 4 have completed and 2 are ongoing. And she also have a membership in the educational professional bodies like World Association for Scientific Research and Technical Innovation, and she also have an International Association of Engineers as a membership, and Indian Society for Technical Education and Mathematics Consortium. And to her feather to the cap, and she has published around 38 papers in the Scopus Index Journal, and she also uploaded many online courses on Coursera. I once again welcome our resource person, Dr. L. Shobana, to deliver our session. Now I hand over the session to Shobana ma'am. Welcome ma'am. Yes, you can start ma'am.
Okay, so good evening to one and all present in the meeting. Am I audible?
Yes ma'am.
Yes, ma'am. Yes, ma'am.
So, first of all, I would like to thank the management of the SIMATS and Dr. Kalai Chelvi for giving me this opportunity. Okay, so with this, thanks. Let me share the screen, check whether it is visible.
Excuse me, ma'am.
Yes.
Yeah, everyone, I will take the one snapshot.
Okay.
So everyone turn on your video.
One second.
Ma'am Rukmani ma'am, just a moment. Okay. Ma'am, let this stop sharing for a while, ma'am, so that we'll take a photo.
Okay.
Ma'am, have you taken photo, ma'am?
Yes, ma'am.
Thank you.
Thank you. Thank you.
Shall I share now?
Yes.
Yes, ma'am.
Yeah, is my screen visible?
Yes, ma'am.
Okay, so the title which I have posted here is Graph-Based Techniques in Secure Network Cryptography. So before going deep into the cryptology, I just want to give some basic definitions of the sequence and the labeling pattern with which we will go for the findings in the cryptography. So as a mathematics professor, let me introduce first our legend, Srinivasa Ramanujam. And he's the great mathematician, as you all know. Okay, and it is his house located in Kumbakonam, and this is Hardy from Cambridge. Okay, so there is a link between this Ramanujam and Hardy. Kalaichali ma'am, is it open to all participants? They can answer, unmute and they can answer.
Yes, madam. Yes, participant, if you
Okay.
madam is asking question and you can able to answer by unmuting yourself.
Okay, so let me give the relationship between this Ramanujam and the great mathematician Ramanujam and Hardy. Okay, so I think you can see the screen. So Ramanujam is a great mathematician of India. Okay, so in the short age, okay, attaining the age of 15, he had mastered various sections in mathematics. He have contributed many findings in mathematics, and this was noted by Hardy. Okay, so Hardy was really impressed by his findings, and he called him to Cambridge. He arranged all the travel for Ramanujam to come to Cambridge, and he was inviting him in the airport. So they both went in the car. So when they were traveling as a mathematician, they want to talk about some numbers. Okay, so Hardy started saying about that car taxi number. So the car taxi number was 1729. So you can see in the bottom of this presentation. So I have written that number also 1729, which is called as Hardy Ramanujam number. Okay. So and Hardy asked Ramanujam, so what is fancy in this number 1729? So there is nothing great about this number. So immediately Ramanujam replied, it is such a fancy number, like it can be expressed as smallest sum of the cubes of the positive integers, like 1 cube plus 12 cube and 9 cube plus 10 cube. So he was greatly admired by the way explained by the Ramanujam, and this number 1729 was called as Hardy Ramanujam number. Okay. And then I wanted to talk about Gauss because his findings make a remarkable research in cryptography. Like they use congruence relations. Okay, number theory focus only on congruence relation. Of course, he is called as Q of sciences and theory of numbers. Okay, and he is Gauss actually. I think you can see this screen, Gauss method. So Gauss, when he was in schooling, so his teacher was asking a question like, what is sum of numbers? So everybody knows. Anyone can say what is sum of n natural numbers? Because you are most of them are CSE students. So you know this, you would have written so many programmings in so many softwares. I am not aware of it. So what is 1 plus 2 plus 3 plus etc. plus n? What is the formula for it? Sum of the n natural numbers. Okay, so it is actually n into n plus 1 by 2. Okay, if anybody is asking the proof, we don't know about the proof. Simply we say it is n into n plus 1 by 2. Okay, so what this teacher did was, she have given a question, like she wants to take rest it seems. So she gave 1 plus 2 plus 3 plus etc. plus 100 and asked them to compute, and she went for a while. Okay, immediately as soon as she was posting the question, Gauss answered the answer. That is, it is 5050. That is 1 plus 2 plus 3 plus etc. plus 100 is 5050. Okay, and the teacher was really surprised because it will take some time, right, to do computation. So he used this different technique. Like let me show in the next slide. So you can see here, first the question given by the teacher was 1 to 100. So it was given here. You can see the mouse pointer, which I'm pointing here. And what he did is he wrote that in the reverse order. Okay, 100, 99, 98, 97 till 1. And you can easily see here, when you add the first two numbers, 1 and 100, it is 101. 2 and 99, it is 101. And simply you will get, when you add the respective numbers, you will get 101. So how many times we are doing? 100 times. And of course, when you add the left-hand side, it is 2s. 2s is equal to 100 into 101. So he gave the answer. And everybody were clapping him and shouting, Gauss, Gauss. So Gauss played in many important findings at the earlier age, in the school level itself. Okay. And I have given an example here, that is sum of 100 natural numbers. Maybe you can follow the same technique for the general case, 1 to etc. up to n, and you can reverse them, add it, you will get the formula. Participants, am I clear? If you have any doubt, you can ask then and there.
Yes, madam. Yes, madam.
Yeah, ma'am. Yes. Thank you. Thank you. So this is how the proof goes. So if as a teachers also, if somebody is asking, we should know some basic things, like these are some elementary things which we can learn. Simply saying sum of the n natural numbers is n into n plus 1 by 2, we can give proof like this. And there are some common views of mathematics. Can anyone say at least 1 or 2 points? I just want to get feedback from the participants. Any 1 or 2 points? What are the common views of mathematics? So you have to be very frank. You don't bother about anything. You just keep in mind that what are the things, common things around you regarding mathematics. Okay, so let me share. So you can see some they'll say maths is hard, some they say it's boring, some they say it's nothing to do with the real life. But mathematics, each and every in daily routine life, you are using mathematics. For example, I'll go with some simple example like buying a ticket in the bus. Okay, suppose if the ticket cost is 12 rupees. Okay, if somebody is giving 15 rupees and getting the ticket, so he need the mental calculation there. Okay, 15 minus 12 is 3, so he has to return back where subtraction plays into the role. Okay, so in each and everything, mathematics plays an important role, but this is the view actually. Okay, so all mathematicians are geeks. And finally, they say, but the truth is, maths is important in crime detection, medicine, everywhere. Without maths, nothing cannot be survived in the life. So next, I want to talk about the sequence. Sequence is very important. Are you familiar with any recurrence relation as a CSE staffs or students? Are you aware of Fibonacci series, Fibonacci numbers?
0, 1, 1, 2, 3, 5, 7.
With the initial condition, we have to fix. So to add the two numbers, basically initially we need two numbers. So that is 0 and 1, right? So when you keep on adding, 0 plus 1 is 1, 1 plus 1 is 2. So I'm coming to that recurrence relation. Before that, I'm going to talk about the sequence. Okay. So sequence is nothing but simply a numbers. There need not be an order also. So you can see here 1, 3, 1, 2, 3, 5, 8. It is a sequence of 5 terms. And similarly, in the second term, you can see 1 cube, 1 that is 3 power 0, 3 power 1, 3 power 2, 3 power 3, and so on. And of course, it is an infinite sequence. Okay. So now comes the recurrence relation. So as you all aware of the recurrence relation, it is nothing but it comes only from the sequence. It is an equation that expresses this an. Normally, we denote the sequence of n general numbers to be an. Okay. In terms of 1 or 4 or more or previous terms of the sequence, namely, we'll start with always a naught, okay, till an minus 1. So this is how the sequence is called the solution of the recurrence relation. So I have given a simple example here. So you can take sequence an, where the recurrence relation, can you see the mouse pointer which I'm moving here? Can you see this mouse pointer?
Yes, ma'am.
Okay. So this is the recurrence relation which I gave here. An is equal to an minus 1 plus 3 for n ranging from 1 to etc. Okay. With the condition, they've given some condition here. A naught is 2. Okay. What do you mean by A naught is 2? When you take n equal to 1 here in this equation, you get A1 equal to A naught plus 3. Where you can substitute A naught value. So your first A1 value will be 5. That is what I have listed here. You can check. In the same manner, you can find A2 and A3. That is what is given here. You should find A1, A2, A3 with the given recurrence relation and the initial condition A naught equal to 2. Okay. So as a staff, suppose if we simply give a recurrence relation, something like this. Okay, and take this. If we go for the class, like if I give the recurrence relation simply like this, take this recurrence relation an equal to an minus 1 plus 3, and the initial condition is 2. Find till a5, a not a1, a2, a3, a4, a5. They simply find and give you the answer. Okay, so what I say is, whenever we try to post some problems, instead of posting them as a problem, give them as the general real-time statement problems. Okay, so you can see the next slide. Okay, suppose that the number of bacteria in a colony doubles every hour. If a colony begins with 5 bacteria, which means that 5 is your initial condition, how many will be present in n hours? Okay, so it is doubling every what is this? Every hour, and the initial condition is A naught is 5 here. Okay. So I think you can see the difference between the previous problem and this problem. So here we have given the recurrence relation and we are asking them to find the solution. We are giving the problem real-time statement problem and we are asking them to find the recurrence relation. So you can see it is given, it is going to double every hour. So the recurrence relation here I have given here is an is equal to 2 into an minus 1. And of course, after finding the characteristic equation, substituting in the formula, we'll get an is equal to 5 into 2. 2 power n. Am I clear? Can you just compare these two problems? Shall I proceed?
Yes, ma'am.
Okay.
Yes, ma'am.
Yeah, thank you. And the next one is, as I told you, I was asking about Fibonacci numbers. Okay, so it was introduced by Fibonacci and the history which I have posted here, where he born and what is his full name, all the details. And he was introducing the book of calculating. And as the ma'am said, the series starts with 0 and 1. So these two are initial conditions and the pattern is repeated over and over. Okay. And this is what is given here. And with the condition, this is your recurrence relation for Fibonacci numbers. With the condition, F0 will be 0 and F1 will be 1. Okay, again, this Fibonacci series, we can project them in the real-time application. Okay, so what this Fibonacci did, like in the 13th century itself, he was explaining this Fibonacci series with a rabbit problem. Okay, you can see here, he is going to consider a young pair of rabbits placed in an island. A pair of rabbits does not breed until 2 months. After 2 months, each pair of rabbit produces another pair each month, in the recurrence relations. And what is the condition is imposing? Assuming that no rabbit ever die. Okay, so you can see here, this is the first pair. Okay, and the same pair in the second month, they are not going to give birth to the new pair. So that is the condition given here. You can see after they are 2 months old, each pair will produce new pair each month. Okay, after 2 months, this old pair is going to produce a new pair. So you can see the number of pairs with the condition that no rabbit pair is going to die. Okay. So first one, second one is 1. And you can see here 2 pairs, 2, 3. So this is how he explained in the 13th century with the help of the rabbit, the Fibonacci numbers. Okay. And see, in each and every daily life, you are seeing Fibonacci numbers. I think you can see the bananas here. Okay, so in the bananas, you can see the sides. This is the half portion of the banana. The second picture, the first picture is the full banana. Okay, so you can see the flat surface. Either it will be 5 or 3. You agree this? Have you ever checked this? I'm not talking about any hybrid fruits or hybrid vegetables. Okay, I'm talking about the normal bananas. Okay, so banana is having Fibonacci number, and you can see in pineapples. Okay, so you can see here the spirals. Okay, how many spirals are there? You can see the green line which I have curved. It is having a curved line here. So 1, 2, 3, 4, 5, 6, 7, 8. 8 is a Fibonacci number.
Yes, ma'am.
Yes, 8 is a Fibonacci number. You can check in the previous slide also. Yeah, you can see here. 1 plus 1 is 2, 2 plus 3 is 5, 5 plus 3 is 8. Okay, so see here in our daily life, we are seeing all these things where the mathematics plays an important role. Of course, Fibonacci is also used by CSE students for so many findings. And see the rose petals. Rose petals are also having, see the outer portion is having 5. 1, 2, 3, 4, 5, and the inner portion is having 8. So this is also a Fibonacci number 5. 8 is also a Fibonacci number. See the cauliflower. Okay, so daily we are using it. Okay, in cauliflower also you can see the orange line and blue line. Where the orange line there are 5 lines. I hope so. 1, 2, 3, 4, and 5. Okay, and the blue lines are placed in the anti-clockwise direction where 8. So 5 and 8 are also again a Fibonacci number. Because why I am showing many pictures is, if it is an offline, I can explain you in whiteboard, or the presentation will be something different. But in the online, at least to attract you, I should put more pictures. That's why I focus on pictures. Okay. And now, what is this 5? Okay, so 5, one of the most significant applications, very important application of Fibonacci sequence is this golden ratio. Normally, we represent that by 5. Okay, so see here, this golden ratio number is always this 1.618034. Okay, let me explain you this. And of course, it was invented by Euclid. Okay, so what he says is you consider this line segment A, B. When you add, it is A plus B. So what they are saying is A plus B by A will be always equal to A by B. That is, you are going to have a constant always 1.618. So let me explain this. So this is also called as golden rectangle. Okay, so inside the rectangle, you will have one small square. So whatever I have explained in the earlier slide is what is given here. Okay. When you divide this by this or this by this, you always get 1.618. And the Fibonacci series also, see here, I am placing them in rectangles. So first one is 1. So when you add one more 1, it becomes rectangle here, 1 and 2. When you add these two, you get 3, which is rectangle. So it increases like this. Okay. And one more thing, as I told you, this golden ratio comes from the Fibonacci number also. Okay, so when you try to divide one number by the other number, you get 1.618. You can see here, I have listed here. The numbers also I have listed here. But what they are saying is till 13th number in the series, you will not get the approx. You will get some values closer to 1.618. Whereas from 14th number, it is fixed. You can see here. You can ask me like 1 by 1 is 1, 2 by 1 is 2, 3 by 2 is 1.5. So it keep on varying till 13 number. So after 13 number, it is fixed. Okay, the value is 1.618. That's why it's called as golden ratio. The Fibonacci numbers also are called as golden ratios. And of course, it is used for this golden ratio is used for in various applications like window cover, file cards, ancient buildings, so many things. Okay, so let me show you some pictures. See here, Leonardo da Vinci. So you can see the picture here, and you can see how it is split. As I showed you that golden ratio rectangles. Okay, with the squares inside. So the golden ratio is introduced in the while creating this picture of Leonardo da Vinci. And this is the instrument invented by Levin to calculate the golden ratio value, that is 1.618. So you can use this machine and you can calculate the golden ratio. So let me show you few pictures. See, you can see the distance, the larger portion. This is your larger portion and this is the smaller portion. So when you try to calculate, you can take your scale and you can take the centimeter, calculate this. This the larger portion divided by the smaller portion will be 1.618. See, in our face itself, we have golden ratio. Eyes, you can see this is the larger portion. This is the smallest portion. Okay. Baghdad city gate. See, you can see here. This is your largest portion. This is the smallest portion. When you divide one by the other, you get 1.618. Okay. Dome of St. Paul, London, England. Great Wall of China. You can see here the upper portion they are showing. This is your larger portion divided by smaller portion gives your golden ratio value. Car, in car. So in the lady structure, tap, bird, insect, flowers, leaf, and in our human hand, you can see here, see, first they have divided. In the next picture, they have given in the measurements also. Like you take these two, when you add these two, you are getting 2. And when you add till this is actually the bone of our finger. So it is going till 3, then you measure this 5, 8. So even in our, so the entire body is having golden ratio value. Okay. So till this you have any queries, let me know.
Ma'am?
Yes.
Good evening, ma'am.
Yeah.
So the Fibonacci, you said no that using that chicks, that rabbit.
Yeah.
Can you explain that one more time?
Yeah, it's very simple only. Let me explain you.
Thank you, ma'am.
Once again, I'm moving to that slide. Yeah. See, this is the first pair, right?
Yes, ma'am.
Okay. The same pair retains the same in the next month also, because what is the condition after 2 months only they have to the new breed.
Okay, ma'am.
Okay, so this breed will retain as such, and and the third month you will have one pair of rabbit. Along with this rabbit, you will have one more pair of rabbit.
Okay.
You can see the condition here. After they are 2 months old, each pair will produce one more pair. That is the condition. Now you got it. So this is your old one. After 2 months, it is going to produce one more pair. Got it?
Yes.
Now the count is 2. Similarly, you have to calculate.
Okay, ma'am. Okay, ma'am. Thank you.
Okay.
Minus 56 into minus 2.
So now we are going to enter into the cryptography part. So for cryptographic technique, I need a graph theory concept called graph labeling. Let me move there. Okay. So as I'm a mathematician, of course, I'm focusing on graph theory. My students are doing research in graph labeling, chemical graph theory. So our focus is now on graph labeling. Okay. Graph labeling. Graph means you will have in your mind that you will have vertices and so-called edges. So you will call in the CS terminology like nodes and links. Okay. So graph will have vertices and edges. What is that labeling? We are going to label the vertices and edges. Okay. So how come you are going to label? One part is you can label the vertices alone. The other part is you can label the edges alone. And the next one is the possible way of labeling is you are going to label the vertices and edges together. Okay. Of course, this labeling was introduced by 1967. So I'm not going to read whatever I have given in the slide. I'm going to just give you the gist what is there in the slide. Okay. So whatever I told is given here, like the labeling of graph is subject to labeling the vertices or edges subject to certain conditions. Of course, it is going to have applications in so many areas which I've listed here, among which we are going to see now is communication network. Okay. And you can see umpty number of various labeling patterns in dynamic survey. You can just type in Google dynamic survey of graph labeling by J.A. Gallian. So you'll have around 200 plus labelings in that. Okay. So every year you will be keep on updating the labelings. You can see this reference. And the graph labeling was originated with the magic labeling, then followed by anti-magic, face magic, all by magic. Okay. So I'm not going to focus on all the remaining labelings. I have made an arrow here, which means I'm going to focus on magic labeling. Magic is nothing but we are going to label the vertices and edges. Okay, we are going to label the vertices and edges in such a way that when we sum, we will get the magic constant. Okay. So you can see here, it is all the mathematics terminology. V union E2, this means 1, 2, 3. What is this cardinality of V union E? Counting the total number of vertices and edges. Till that you have to label. Maybe I can show you example where you will have a clear idea. So what is the condition here is such that for all edges xy, f of x plus f of y plus f of xy is constant. So what is this f of x? We are going to label that x vertices plus we are going to label the y vertices plus we are going to label the edge. Xy means edge. I think this is clear now. So once this is clear, we'll move on to the graph. Okay. So let me show you this graph. Can anyone say everything is clear in this graph? Of course, we call this as the cycle graph with 7 vertices. And I've labeled both. You can see the number I have started with 1 here. Okay, it is not in order actually because I have to bring the magic constant. What is the magic constant given here in the graph? I told you magic is nothing but you will get same number. Okay, what is the same number which I have given in this slide?
19.
Very good. So it is openly given, right? So you can easily say. So 19 is the constant. So what I have done here is I have labeled both the vertices as well as edges. You can see one is placed here, 2, 3, 4, 5, 6, 7. So once it is over with this vertices, I'm going to start labeling the edges. You can see in the reverse order, I have labeled 8, 9, 10, 11, 12, 13, 14. So can you say how this 19 came?
14 plus 4 plus 1.
Exactly. So it is 4 plus 14. So which means we call this as total labeling, 1-1 labeling. What do you mean by 1-1 labeling? we are going to label the vertices as well as we are going to label the edges. 1, 0 is we are going to label only the vertices. 0, 1 is we are going to label only the edges. Okay. So I think now you can see the variation. Here this labeling pattern involves 1, 1. As ma'am said, it is 4 plus 14 plus 1, which is 19. And you can see everywhere 1 plus 13 plus 5 is 19. So we call this as magic constant, and that constant is 19. Okay. And there are umpty number of magic total labelings. Let me show you this example. We call this as super edge magic labeling for the path graph. Okay, super edge magic labeling. So can you say what is the magic constant here?
16.
Very good. So you can see here, like it's 1 plus 11 plus 4. Actually, it is total labeling. We have labeled both vertices and edges. So 1 plus 11 plus 4, 16. 4 plus 10 plus 2, 16. And it goes on like this. So the magic constant here is, as ma'am said, it's 16. The other graph, so it is called as super vertex magic. So you can see the difference. Here it is edge magic. Here it is vertex magic. Can you say what is the constant in the second line? We call that as path graph, P9.
30, ma'am.
No? Are you getting 30 everywhere? Okay, so I think you would have not been aware of it. So you can see this. So it is, see, there is a slight difference. It is vertex magic. Vertex means you take the first vertex. Okay. The first vertex label here is 17. Okay. So, and you have to add all the edges that are incidental to this vertex. Okay. So what is 17 plus 4?
21.
21. So let me take any other vertices here. So let me take this vertex. Okay, so each label is 11 and the two edges are incidental to it. So it is 3 plus 7 plus 11. What you get?
21, ma'am.
Okay, so 21 is the magic. So can you see the difference here? First one is edge magic, which means we are going to consider the entire edge. When you consider the entire edge, we are going to consider the vertices label along with the two adjacent vertices label also. Whereas here it is vertex magic. So you focus on vertex, one particular vertex, that label plus sum of all the edges that are incidental to that vertex we have to calculate. Okay. There are umpty number of magic labeling, as I told you, so I don't want to discuss this. And anti-magic is, the difference will be, like, let me explain you one and move to the cryptographic technique. So you can see here the labels are 1, 2, 3, 4, 5, 6, and they have labeled 7, 8, 9, 10. So it is edge anti-magic total labeling. Okay. So edge anti-magic total labeling. So when you add this, what is this 12 and 2? Can you say? Anti-magic is the constants will be different. You can add this. So what you are getting? 7 plus 4 plus 1. What is in the sum?
Yes, ma'am. 12.
12. You can sum this. 8 plus 4 plus 2. What you are getting?
12. 14.
Yes, 12, then 14, then 16. So you can see the difference is 2. So that is what is given here. 2 difference and the starting number is 12. Okay. So I think you can see the variation now. Magic is throughout you should label in such a way that you get single number magic constant. In anti-magic, it is not that you have to get in this series 12, 2. Even if you are not getting it, we call that as simply anti-magic. If you are getting like this, we call that as it is going to have some arithmetic progression. So it is called as AD anti-magic. Okay. So I'll just skip this. Phase magic labeling. As I was explaining about magic labeling, phases. The phases you can see here. There are 1, 2, 3, 4. 4 phases with 3 vertices. That is cycle. And one phase is the interior cycle with 4 vertices. Okay. So all these, what is phase magic labeling? It is nothing but all the n-sided phases should have same constant. You can see here I have labeled with 34, 34, 34 everywhere. So when you add this together, you get 34. Okay, all the C3 triangles. So all these will have one constant. And of course, I told you n-sided, right? So these exterior are 3-sided and inside is the 4-sided phase, which is going to have a different constant. You got the point. Even though the exterior portion are having one constant, the four-sided face is going to have one constant. It is face matching. N-sided should have same constant. Okay. And next, my supervisor, Dr. Bhaskar Babuji, he introduced edge by magic total labeling, 1,1 edge by magic. And you can see here, I have considered the same cycle. Earlier, I was showing you C7, it is C6 now. When you try to add, you get two different constants. One is 16, the other one is 17. Okay. And again, face by magic is, you will get for the n-sided faces, you will get two constants. Okay. And face anti-magic. Once you understand magic and anti-magic, it is same for face and the other. This is very important. Strong face, which was introduced by my supervisor, Professor Bhaskar Babuji, Anna University. Okay. So let me explain you with the example. So we call this as planar graph. Okay. So this is the basic PL5 graph. And after imposing strong face, you got this figure. Okay. So can anyone analyze what is the difference between these two graphs? That's why I have placed the original graph also by the side. So what is the difference between this graph and this graph? We call this is simply PL5, planar graph PL5. This is strong face of PL5. What is the difference between this graph and this?
One vertex is connected to all the other vertex.
All the other?
Strongly connected.
Okay, partially right. So what ma'am
Is it a complete graph, ma'am?
No, it's not a complete graph. So what we are going to do is, we are going to introduce one new vertex inside one cycle. Okay. So you can check here. So you can introduce one vertex here. Okay. And it should be connected to all the other adjacent vertices. Similarly, here one vertex. You can see the mouse pointer. So I'll place one vertex here and I'll join here. I'll place one vertex and I'll join here. Likewise, you have to introduce for all the closed cycles. Am I clear now?
Yes, ma'am. Yes, ma'am.
Okay. Okay. So this you keep in mind because we are going to do square grid encryption. Okay. So the application of graph labeling, it has its various applications in domains like cryptography, number theory, formal language, and automata, and so on. So now we are going to see cryptography. Okay. So I think as a CSE students, you know the basic things like what is encryption, decryption. So I'm skipping this. So of course, this is very important. Plain text will be converted to encrypted form. And then we are going to decrypt it using some key and we are going to get back to plain text. As I told you, the magic constant, we are going to use this magic constant in our finding. So as I told you, we are going to talk about the grid graph. So as I was showing for planar graph, here I'm going to show for square grid graph. This is the normal P4 cross P4. As we discussed earlier, for each and every closed C4 cycle, we call this C4 C4, and you can introduce a new vertex inside joined by the edges. Is this path square grid path graph clear? This is normal grid. This is after introducing the new vertex. That is, this is strong face of the square grid graph P4 cross P4. This you keep in mind. Okay, so now what we are going to do is we are going to use the encrypting technique. Most probably 90% we will be focusing only on encrypting the messages. Here we are going to encrypt the number. Okay, so what I'm going to do is my input is simply a square grid graph. Okay, Pn cross Pn with the condition n should be a multiple of 3 always. Okay, I'm going to post that graph. Okay, and of course it is a directed graph. So you will have a direction. What is you have to collect the number, secret number from that graph. That is what we are going to do here. So to do that, we are going to divide the given number into 3 components. Okay, with the condition residue 0, residue 1, and residue 2. Okay, so that's what I've given here. You partition the number into 3 parts. Okay, I'm not aware whether you know what is residue. Residue Zn, you are aware of it. What is it Z3 means? So the Z3 will have the elements 0, 1, and 2. Okay. Suppose if I say 7 modulo 3, 7 modulo 3. So the number is, when you try to divide 7 by 3, the remainder is 1. So you'll get 1. So whatever number you take, when you try to divide by that n, you get 0 to n minus 1. Okay. So am I clear with this Z3? Z3 will
Yes,
have
ma'am.
elements 0, 1 and 2 alone. Whatever new number you take 100, you take 1000, you take 50,000. When you try to divide by 3, it leaves a remainder. That remainder will be either 0 or 1 or 2. That you keep in mind. So this is the square grid graph vertex pattern and edge pattern, and these are the number of phases. Okay, it will have. This is only for square grid. Okay, so what I'm going to do is I'm going to label them in ordered pairs. So to confuse the opponent, or we call eavesdroppers, I'm going to introduce the labels, not the single label. I'm going to place them in orders. Okay, that you keep in mind. And there should be some key, right? My key here is K. Okay, my key here is K. I'm going to find the bound for that K. Okay. So there are two conditions. As I told you, whatever number I'm going to take here will be multiple of 3 again. So when n is congruent to 0 mod 3, that is multiple of 3. There are two cases. One will be odd, the other one will be even. Okay, when I say n congruent to 1 mod 2, it is odd number. And I have got a result that my k should be greater than 4n square minus n plus 1. When you go to the second case, that is when it is multiple of 3 again, your n is multiple of 3 at 0 mod 3. This is even. This is even. Okay, in that case, I am getting the condition k should be greater than some bound. That is missing actually. The final k I have written here. Always this key value k should lie between 5n square minus 4n plus 2 and 8n square minus 12n plus 9. So n is nothing but, for example, I showed you P4 cross P4 where n value is 4. So you can substitute the n value here and you can find the upper bound and lower bound. Okay. So whatever I told you is given here. So they're going to partition into 3 components. So you will get 3 sets. V1. So if it is 1 modulo 3, if it leaves the remainder 1, we put all those numbers in V1. If it is going to leave the remainder 2, we put all those in V2. If it is going to leave the remainder 0, suppose if you take the number 9, when you divide by 3, it leaves the remainder 0. So all those numbers should be placed in V3. And see how many partition we are going to do here, the edge partitions. So we are going to do 6 partitions, E1, E2, E3, E4, E5. And I have defined the edges here. Okay. So this is the labeling pattern which I'm going to do. So f of vi is all the vertices I'm going to label with the condition I minus 1 mod 3 comma I. Okay. Suppose if I'm taking first vertex to be V1. V1 now, what is the condition? I value is 1. When I take I to be 1 here, it is 0 mod 3. So my first order pair will be 0 comma 1. Is this clear? When I take I equal to 1, it's 0 comma 1. Am I clear?
Yes, ma'am. Yes, ma'am.
Similarly, you have to label all the other vertices in the given method. Okay. And the edge labelings also I have given here. Let me show the edge labelings. Okay. The orientation. So I told you direction, right? So the direction should be Vi, Vj. So if I'm going from I to j, when I try to add I and j, if I'm getting 0 mod 2, the direction will be like this. Otherwise, it will be in the opposite direction. That is, I've written Vj, Vi. Okay. And the edge labeling will be P comma Q, where the first one is, I told you, we are going to divide into 3 components, NM1, NM2, NM3. Okay. So that when you divide by 3, and this is nothing but flooring. So you have to consider the whole number. That's why we are taking flooring of that number. And Q can be placed with this bound, with this condition. Okay. And one more condition. So if I mod 3 is equal to j mod 3. So when two numbers, when you divide by 3, if it's going to leave the same remainder, the labeling will be, the first component will be always 0, followed by the edge labeling. Otherwise, if this condition is not satisfied, then we move to this condition. So the decryption formula is this. So first I have showed all the encryption techniques. So this is the formula for decryption and to get the number. So let me explain you with the example. So I think can you see this example?
Yes, ma'am.
Okay. So the secret number which I'm going to encrypt is 369. Of course, this is divisible by 3. That is the condition which I gave already. Okay. And I'm going to see one thing you have to understand in strong phase. So you take any graph, when you try to apply the strong phase concept, all will be C3 cycles. You agree this? I
Yes,
showed
ma'am.
you
Yes,
a
ma'am.
planar graph, right? So it will be
Yes.
C3 cycles. There will be empty number of C3 cycles, among which we are going to take only one C3 unicyclic where our secret number is placed. That is our technique here. So you try to divide this into 3 components as I told you. So we are going to divide this 369 to 123, 91 and 151. So how we are dividing, that is the technique. Like we have to divide in such a way that you should get one remainder to be 0, one remainder to be 1, the other to be 2. Okay. For example, if you take this 123, when you try to divide by 3, so what is the remainder? 0. Right. So it goes 41 times. Okay. Likewise, you have to calculate here. You will get 1 here and you will get 2 here. Can you see this graph?
Yes, ma'am.
1, 2, 3, 4, 5, 6. It is P6 cross P6. Okay. And the vertex labeling are labeled like, see, everywhere we labeled in ordered pairs. So this is 0, 1, 1, 2, 2, 3. So this is first component here. Let me explain with the first line. First line you can see here. So it is 0, 1, 2, 0, 1, 2, which means we are going to consider that modulo value 0, 1, 2 as a first component. And the second component are edges, that labels 1, 2. Because it is 6 cross 6 till 36, we will place here. You can see the mouse pointer. 1, 2, 3, 4, 5, 6, and 7, 8, 9. So first we will fix all the row vertex labels. Once it is ending 36 here, we have to label here 37, 38, 39, and it goes on. Okay. And what is the condition which I gave you? The uni direction condition. I mod j is equal to j mod j means we have to take the first component to be 0. For example, let me consider this line. Okay. So it is, what is this? This is I. 1 is I and the 7 is j. Okay. So 1 mod 3 is 1. 7 mod 3 is 1. So both are going to leave the remainder 1. So therefore, the first component should be placed to 0. So that is what is given here. Let me show that condition. Yeah, can you see here? If not so, we have to use this component. Okay. So and let me show you what is these numbers 41. This 41, 30, 51. What are these numbers? Can you guess? 41, 30, 51. It is repeating here. 41, 30. I showed you one number, right? So when you divide 123 by 3, what is quotient? You know quotient and remainder, right?
41, ma'am.
Very good. So when you divide 123 by 3, it is 41. 91 by 3?
Plus
30, remainder 1.
Yeah. So first one, keep in mind, first one is 41, second one is 30. Third one? Third one? It goes 5, 3, 5, then 51. Okay. So these are the numbers.
51 remainder 2.
Yeah. We are focusing only on the quotient here. It is 41, 30 and 51. Similarly, you have to place all the things. And how come you fix this direction? Suppose when I take from 1 to 2, so 1 plus 2 is 3. 1 plus 2 is 3, which is an odd number. So I have to put the direction in the opposite side. I should not take from 1 to 2. Am I clear? I'm taking this vertex 1 and this vertex 2. 1 plus 2 is 3, which is an odd number. If it is an odd number, you have to place the direction in the opposite side. This condition also it is given here. I think you can check here. Okay, likewise, you have to place all the directions, labels in this graph. You can see some may have unidirection. I think you know what is unidirection and opposite direction. Okay, so you can see only one triangle I have marked with red line. Yes, in the bottom of this grid. Can you see this triangle marked with red line?
Yes, ma'am.
Yeah. So why I have marked this is, see in this total strong face of the path graph P6 for square grid graph P6 cross P6, you have both unicycle direction and some in the opposite. It will not be an unicycle C3. Among the unicycle C3, this is the one triangle where my number is hidden. Okay, so this triangle you can see here. Okay. 41, what is this number? These are all the components here. First component 41, 30, 51, and the label is 102. Okay. So I have taken that triangle and I have shown here. And what is the formula for decryption, which I have showed you in the algorithm? It is the summation of 3 times f of vi vj plus that vertex alone. Okay, so you can see here. So what is this actually? 3 into this 41 plus 1. When you consider this edge, it is 3 into 30 plus 0. When you consider this edge, it is 3 into 51 plus 2. So when you sum all these, you get 369, which is a secret number hidden in this strong face of the square grid graph P6 cross P6. Okay. So these are the analysis, what we did there. We found the bound for key and we got the number. And of course, the total number of phases here, the strong phases here is given by 4n square minus this many phases it has. Obviously, we are checking only the phases, right? The cycle will have one phase. One C3 cycle will have one phase. So how many phases are there? 4n square minus 8n plus 4. Obviously, the first running case time will be order of n square. So this again, you all know it's a practical application where in the ATMs you can use numbers. So you can use this technique here. And in military base, they use both the messages, transforming the messages in the number form as well as message form, and even banks. Okay. So these are the applications of the encryption technique which we did. And these are the references. In recent years, many are doing applications with their findings. These are all the references, and of course, my supervisor, as I told you, Bhaskar Babuji, he did many findings in 2017, 2017, and one more paper I'll show you. Yeah, see, this graph coding technique he did in 2005. Okay, and recent with my students, we did so many papers, and of course with Professor Bhaskar Babuji and Ismail Gangul. And I showed you like the grid graph, right? This I have published here in encryption numbers through square grid graphs in 2018. And thank you so much. If you have any questions, let me know.
It was a wonderful session, Shobna ma'am. I also want to communicate to the participant, kindly fill the feedback form, as well as any query is there, you can unmute yourself and you can ask. But don't forget to fill the feedback link. It is posted in both YouTube and as well as in this chat window. Kindly.
Yes, someone is trying to ask question, it seems.
Can you hear me?
Yes, sir. Yes.
This is Dr. Nandagopal. I just wanted to know about your recent work in the platform which you have worked in the graph which you have shown. Any practical application in data analytics give one example application?
So, as I told you, I am a mathematics professor. Right now, we were working on only chemical graph theory, sir. Chemical graph theory, like they're taking the anti-drugs, and we are implementing our results in the anti-drugs, and which ones, because when you take anti-Parkinson disease, so you will have more medicines, right? Someone will give some medicine which is adopting your body. So likewise, we are collecting all the medicines and using the topological indices, we are finding which one will be the best. Okay, but data analytics, I'm not aware of it.
Series of, which you are saying, the series of the medicine with the same components with the different names or what? How you?
Yeah, anti-drugs, you will have different anti-drugs. Now, suppose if you take for fever, we will have paracetamol, crocin, something like that. But everything, you will have only small variations in their compounds, chemical compounds. So we will collect all the anti-drugs. We'll try to incorporate our concept, and we'll say, we cannot say that is best. We just give suggestion. It should be worked by the chemist in the lab, which we cannot do. So we'll go with that many findings, such findings, and we'll finally we say these are all, as a mathematician we are doing it, but as a chemist, the chemist should do that in the lab.
Right.
Thank you, sir.
டாடி ஒரு நாள் சொன்னாங்க இந்த மாதிரி சின்சா நகர இடத்துல ஒரு நாள் ஹெஸ்ரான ஓட்ட விட்டுட்டா பழகி.
Anybody else? Any questions?
Ma'am, it was a wonderful session. Now I call Dr. Selva Ganapati sir to give the vote of thanks.
Thank you, Kalaichilvi ma'am.
2 minutes, ma'am. Sorry. Selva Ganapati sir.
So thank you for all the participants. And right now I'm noting all the messages.
Okay,
Thank you so much.
sir. On behalf of Department of Data Analytics, Saveetha College of Liberal Arts and Science, I thank our resource person and all the participants who are actively participating in this 1 hour plus 10 minutes. So I'm very happy to see this interactive session is going on well. Thank you, Dr. L. Shobna ma'am and the participants too. Within 10 days, likely you will get your certificates. Thank you all. Thank you, ma'am. Yes.
Thank you once again, the management as well as the participants. Thank you so much.
Thank you. You can leave.